Good day everyone! Today, we will present the design of the dilute phase pneumatic transport system using Excel. The design of the dilute phase transport system involves selection of a combination of pipe size and gas velocity to ensure dilute flow, calculation of the resulting pipeline pressure drop, and selection of appropriate equipment for moving the gas and separating the solids from the gas at the end of the line. In today's presentation, we'll know more about the programming, the overview of the codes used, second, the user interface of the calculator, and lastly, the work example.
This is the code for the Excel app. This code has three parts: function, main sub, and solver. The function part of the code contains all the equation necessary for the pneumatic transport design. This is the main sub procedure, which I named final design. In here, I defined all the necessary variables and assigned the results from the function part to these variables. After assigning values to the variables, the main sub then instructs Excel to write these values to specific cells. Lastly, the solver procedure instructs Excel to do the iterative calculation for the slip velocity. One last thing to note is that before using the Excel app, check first if the solver add-in is activated. Then, in the VBA, go to Tools and click References. Then check Solver, otherwise this Excel app will not work.
The Excel app that we have created let the user calculate the important parameters in the design of dilute phase pneumatic transport systems such as pipe size, air flow rate, air superficial velocity, saltation velocity, solids loading, and total system pressure loss using the data given, which are inputted by the user in corresponding unit indicated by the app. The user input data requires solid mass flow rate, solids density, air density, air viscosity, mean particle size, vertical distance, horizontal distance, number of 90 degrees bends, and pipe inside diameter. Note that this automation assumes that all the initial acceleration takes place in the horizontal sections. Only the data given table and pipe size pressure loss table can be changed by the user. The user should manually input the total pressure drop for the pipe size pressure drop table and click the Solve button to perform the automation.
For the work example 8.1, the problem goes like this. Design a positive pressure dilute phase pneumatic transport system to transport 900 kg per hour of sand of particle density of 2,500 kg per meter cube and a mean particle size of 100 micrometer between 2 points in a plant separated by a 10 meter vertical distance and a 30 meter horizontal distance using ambient air. Assume that 6 90-degree bends are required and that the allowable pressure loss is 0.55 bar. Given in the problem are the solids mass flow rate, which is equivalent to 900 kg per hour or 0.25 kg per second, 2,500 kg per meter cube solids density, 1.2 kg per meter cube air density, 1.837 times 10 to the power of -5 pascal second air viscosity, mean particle size of 100 micrometer or 0.001 meter, 10 meters vertical distance, 30 meters horizontal distance, 6 90-degree bends, and standard pipe inside diameters which is equivalent to 78 millimeters, 63 millimeters, 50 millimeters, and 40 millimeters. After that, we will input the given data in the calculator. Next is we need to compare the calculated and allowable pressure losses by repeating the calculation procedure for a range of pipe sizes. If the pipe diameter is 78 mm, the pressure loss is 0.210 bar. For the 63 mm pipe diameter, the pressure loss is 0.322 bar. For the 50 mm pipe diameter, the pressure loss is 0.514 bar. Lastly, for the 40 mm pipe diameter, the pressure loss is 0.815 bar. Computed pressure loss must be close enough but should not exceed to the allowable pressure loss of 0.55 bar as stated in the problem. In this case, we would select the 50 mm pipe, which gives a total system pressure loss of 0.514 bar. The design details for this selection are given below. That's all, and thank you for listening.